Hello and welcome back. In this video, I want to discuss how we solve problems that involve pulleys and ropes. The first thing I need to mention is that the force that is carried through a rope is called tension. So for example, if I have, say, some box here and I've got a rope attached to it, and I apply some force to one end of this rope, this force will be carried through the rope and there will be a force exerted on this box. So the force that is carried through the rope is called tension. Now when we solve problems involving pulleys and ropes, we're going to make the following assumptions. The first assumption is that the tension will be the same everywhere inside the rope. So for example, if I apply a force F to one end of this rope here, then the force at the other end of the rope is going to be the same. Basically, what this assumption is saying is we're assuming that the rope is massless. The second assumption is we'll assume that pulleys only change the direction of the tension, but not the magnitude of the tension. What this assumption is assuming is it assumes that the pulleys are both massless and frictionless. The final assumption we'll make is that the ropes that we deal with are a fixed length, so that when one end of the rope moves by a distance delta x, the other end of the rope moves by the same distance. What this assumption is assuming is it assumes that the rope does not stretch. Now, when we're solving problems involving ropes and pulleys, a good idea is to set up a coordinate system where when the rope moves in one direction, that's one of the directions of your coordinate system, and the rope moves in the other direction is another direction of the coordinate system. What this means is that a lot of times your coordinate systems will curve with the rope. So for example, here I've got a mass sitting on a table, another mass that's hanging off of the table, and they're attached by a rope that passes over a pulley. So what I might do is I might call this direction here the positive direction. Notice that this axis kind of curves as it follows the rope. Okay? This is a very convenient type of coordinate system to set up, because when we look at this we can see that the motion is going to be along this curved path. Okay, this object here is moving down, but this object is moving to the right. And we can see that when this object moves in the positive direction, that's down, this object over here moves to the right, which is also the positive direction using this curved coordinate system. So another example, if I had, say, something like this, say two masses that are on opposite sides of a wedge shape like this, and they're attached by a rope that passes over a pulley, maybe I'd call this direction my plus direction. Okay? So when this mass is sliding down this ramp and this mass is being pulled up this ramp, we would call that the positive direction. So let's go ahead and look at a few examples. The first example is considering an Atwood machine. And basically what an Atwood machine is you take two blocks and you attach them together with a rope that passes over a frictionless pulley. And the question here asks us to find an expression for the acceleration of these blocks in terms of the masses of the two blocks and the acceleration due to gravity. So the way we solve a problem like this is the first thing you do is you draw a free body diagram for the two masses. So for mass m1, there are two forces acting on the object. There's the force due to gravity that I'll call F sub g comma 1. I'm using a subscript here, 1, because I have two masses, so I'll have two forces due to gravity. And then there's the tension. And then the second block, we have this M2 here. And similarly, there's the force due to gravity that points down. And the tension that points up. Now these two tensions are the same, right? Because this is the tension in the same rope, and one of our assumptions was that the tension inside the rope is the same everywhere. So the tension pulling up on this mass is equal to the tension that pulls up on this mass. Now, as you can see here, I've drawn this so that my coordinate system is set up so that when the masses are moving like this, this is the positive direction. So when this mass is being pulled up, that's the positive direction. When this mass here is falling down, that's the positive direction. So here for this mass, down is the positive direction, and for this mass, up is the positive direction. So from here I can apply Newton's laws to each of these masses separately. So here we have this net force acting on mass 1 is equal to mass 1 times acceleration. So this is tension minus the force due to gravity on box 1 is equal to mass 1 times acceleration. Here, the positive direction is in the direction of the tension, so the sum of the forces on box 2 is going to be plus the tension, because tension points in the positive direction, minus the force due to gravity, because that points in the negative direction for this box. So now we have a system of two equations and two unknowns. The two unknowns are the tension and the acceleration. So whenever you have a system like this where you have two equations and two unknowns, but we're only asked to solve for one of the unknowns, the first thing you do is you solve for the unknown that you don't care about in terms of the other one. So here I don't care about tension, so I'm going to solve for tension first. So if I solve for tension first, let me go ahead and add tension to both sides. Add tension to both sides. Then I get m1g is equal to m1a plus t. Solving for t, I get that t is equal to m1g minus m1a. Plugging this into the other equation gives me an equation that only has one unknown, the acceleration. So tension is m1g minus m1a minus m2g is equal to m2a. Now, what I want to do is I want to take both of the terms that have acceleration and move them to the same side of the equation. So I'll add m1a to both sides, and then I get m1g minus m2g is equal to m1a plus m2a, or m1 plus m2 times a. So dividing both sides of the equation by m1 plus m2, I can see that my acceleration is equal to m1g minus m2g divided by m1 plus m2, or m1 minus m2 divided by m1 plus m2, all of that times g. So this is the acceleration of an Atwood machine in terms of the masses and the acceleration due to gravity. Moving on to the next example. This example, we have an 8 kilogram mass that is placed on a frictionless inclined plane. It's 30 degrees above the horizontal. Attached to this mass is a rope that passes over a frictionless pulley at the top of the ramp, and then hanging from the other end of the rope is a mass M2 that's 22 kilograms. So because this mass M2 is much larger than this mass M1, this mass M1 is going to be pulled up the ramp, and I'm asked to find what that acceleration is. So since I know that M1 is going to be pulled up the ramp, I choose to call this direction here the positive x direction, where the mass M1 is being pulled up the ramp and M2 is falling down. Again, the first thing we want to do is we want to draw free body diagrams for the two masses. So for mass M1, here we have a mass that's on a ramp. And there are three forces acting on this. There is the force due to gravity that points down. There is tension, which is pulling the mass up, and then there's the normal force. So all I want to do is find the forces that point in this positive direction here. Okay? So the sum of my forces acting on M1 in this direction is equal to mass 1 times acceleration. And the sum of the forces acting in this direction, well, there are two forces that act in this direction. Tension is parallel to the positive direction, and then I have a component of my acceleration due to gravity, this component right here, that opposes the motion of the block up the ramp. And this right here is going to be mg sine of theta, right? Remember that this angle here, theta, is equal to this angle here. And this side of the triangle is opposite the angle theta, so the component of gravity that opposes the motion of the box up the ramp is mg sine theta. So here we have the sum of my forces. This is the component of the force due to gravity that is pointing in, I guess we'll call this the x direction, right, minus that because it's in the negative direction, plus the tension is equal to m1 times a. And then finally we can say that this is minus mg sine of theta plus tension is equal to m1 times a. Likewise, we have the other mass, m2, and there's only two forces acting on this. There's the tension that pulls up on the mass, and then there's the force due to gravity that's pulling down. So if we sum up the forces acting on mass 2, again this has to equal m2 times a. The two forces are, so again the down now is the positive direction, so we have plus the force due to gravity on box 2 minus tension is equal to m2 times a, or m2g minus tension is equal to m2a. So these are our two equations. Let me write them again. So we've got minus m1g sine of theta plus tension is equal to m1a. And the other equation we have is let's see, it was m2g minus tension is equal to m2a. Okay, so again we have two equations and two unknowns, and the only thing I'm asked to solve for is the acceleration. So again, I can choose either one of these equations to solve for the acceleration. I'm sorry, to solve for the tension. So I guess I'll use this equation here. So if I add m1g sine theta to both sides, here I get tension is equal to m1a plus m2g sine of theta. Plugging this into the other equation, I have now m2g minus tension, which is minus m1a plus m2g sine theta is equal to m2 times a. And now this minus sign will distribute. So actually, let me just get rid of this parentheses here. And what we have is this is a minus here, and then we'll have a minus here as well. So again, we're trying to solve for a, so we move everything that has a to one side of the equation. So to do that, I would add m1a to both sides of the equation. If I do that, then I see that this is equal to m2g minus m2g sine theta is equal to m1 plus m2 times a. I realize now I must have a mistake in here. Oh, this of course should have been m1. I don't know how I got an m2 in here, right? This was, over here on the left, this is just the equation for mass 1. And I was supposed to add m1 sine theta to both sides, and I turned that into an m2. So over here, of course, this should have been an m1, and this should be an m1 here as well. So finally, dividing both sides by m1 plus m2, I get that the acceleration is equal to m2g minus m1g sine theta divided by m1 plus m2. And all of these values I know. I know m1 and m2. I can calculate sine of 30 degrees, and I know g is 9.8. So looking at my cheat sheet, if I plug all these numbers into a calculator, what I should get is 5.88 meters per second squared. So that's the acceleration of this box here going up the ramp, and the acceleration of this box falling down. So now I want to look at just one last little example, because this is pulleys and ropes most of the time are used to gain what's called a mechanical advantage. And I want to kind of look at just how this works. So over here on the right, I have this example where I've got a person who's standing on a platform, and you can see there's this rope he's holding. The rope goes up, it passes over a pulley, it comes back down, and then it passes over a pulley that's attached to that platform, and then it comes back up again and it's anchored up here. And the question is, if the person plus the elevator, so this whole thing here, weighs 1,500 newtons. How much tension does he have to apply here to this rope? How much force does he have to pull down on the rope to lift this whole thing up at a constant velocity? Or in other words, how much force does he have to apply just to hold himself there? So looking at this, you might say, well, he's got to pull up with his weight, 1,500 newtons. But that's not really true, right? Looking at this, we can see that there are three forces pulling up on this platform. The tension is applied at three different places. So actually, the total force applied to this whole platform is 3 times the tension. So the force that he has to apply to lift himself up is actually 1/3 of the total weight of this thing, right? Another way to see this, right, so we have this man who's standing on the platform, so he's holding this rope, the rope goes over a pulley, comes back down, does this kind of thing. Okay, so here we're considering this rope that can, be pulled, but what if I just had a box and I had, just say, 2 ropes that were attached to this box? I'm sorry, what if I had a platform and I just had 2 ropes attached to the platform? Well, if this rope has a tension T and this rope had a tension T, we could see that the force being pulled up on this would be 2 times T, right? The fact that this rope is passing over a pulley doesn't matter. It's just as if, right, there was a rope here pulling up and a rope here pulling up. The fact that the rope passes over a pulley when it does this doesn't matter. There's a tension T pulling up here, there's a tension T pulling up here. So the total force that's being pulled up on this pulley is 2 times the tension in the rope. And then of course there's the fact that the man here, is pulling down on the rope, so the rope is pulling up on him, according to Newton's third law, and that force is also equal to the tension in the rope. So that total force caused by the rope here and the rope passing over the pulley is 3 times the tension in the rope. So if this whole thing here on the right weighs 1,500 newtons, then the force that has to be applied and the tension to lift the platform up at a constant velocity is only 500 newtons. Now, one thing I want to mention, and it may not seem very significant just right now, but when we talk about work and energy in the next week, we're going to see that this is really, really important. So when this person pulls down on the rope and moves the rope by a distance delta x, the question would be, how much does this platform move up? Well, what happens is when this person moves this rope down, when he pulls the rope down at distance delta x, this entire length is now shortened by a length delta x, okay? But the entire length is this length plus this. So if he pulls the rope down by amount delta x, this platform only moves up by 1/3 delta x, right? Because this length here is shortened by 1/3 delta x, this is shortened by 1/3 delta x, and this is shortened by 1/3 delta x. So the total amount this whole rope was shortened by is delta x. But the platform only moves up 1/3 of delta x, right? Because each one of these is reduced by 1/3, causing a total length of the rope to be reduced by delta x. But the platform is only going to move up by 1/3 of delta x. So the person has reduced the force that he needs to apply to lift this elevator by a factor of 1/3. But to lift the elevator by a height, delta x, he now has to pull the rope 3 times that amount, okay? So he's reduced the force by a factor of 3, but he has to apply that force over 3 times the distance to cause the elevator to move up by the same height. So this is the last video on Newton's laws, and I think the next video will be on circular motion.